All right, I'm back. My computer crashed out. It just died, and I got the blue screen, so I had to start everything up again. But I'm just about to... I got a message, I think, from someone. Andrew and Alan are probably going to be popping on here, but I got to figure out if I can do the webcam thing. There we go. There's my green screen you can see. I got to do this.
All right.
Hey, I got to find something for my background that I was trying to find, but couldn't because my computer crashed. So, Alan, how you doing?
Doing all right.
Good. Is it my green screen you can see, or is it SpaceX behind me?
SpaceX.
Okay. Man.
I got about a half hour to go.
Okay. So, Deborium, I got to check my... We're just going with this one right here. Okay. We're swimming at the ocean or something. I got to go to my Facebook and see. I think he messaged me. It's giving me a couldn't join call. Okay. And Andrew, let's see. I'll have to... Can you give me your email? And I can send you a link in email because it should work from email. So you could do it in Facebook if you want. Or if you just send me an email at ftupworld, EFTUPWORLD@gmail.com. And then I'll just send... If you send me one, I'll send you whatever. Either way. Then we'll get on there. So let's see here. Do I have this? Okay, I do. All right. Deborium says, yeah, 1 second. Okay, cool. And Alan, I have to go to see you because I think you are not there, or are you there?
Yeah, I'm here.
Oh, okay. Good deal. So what? Where were we? We were talking, and then you had to take a break, and then it was almost like immediate that my computer crashed out.
Well, that worked out.
Yeah. You remember what we were... Whoops. That wasn't supposed to happen. Do you remember what we were doing? Did you see that or no?
Hey, are you on the space station?
Oh, yeah, I should. That's what I should.
You were in the space station for a second.
Yeah. Let's do that right now. Let's see here. I have to go to... or wait a minute. I got a good one. I got to show you. Let's see. Well, I'll do that later. Okay. So I have to just hit this button. And then... Oh, you know what I have to do is I can't have you guys watching me change. So I got to put on a video.
All right.
There. Watch this video and tell me what you think about... you can see the green screen there, so that's kind of screwy. But that shadow right there, that has no penumbra and no umbra. The shadow of my drone. Let me see if I can... Oh, I know what I can do. There. Just watch that a few times while I'm changing into my space station outfit, because it's really easy to do. I just have to take a rocket up there. But if you think of the shadow of the eclipse, I'm
gonna put on my white lab coat.
Oh yes, you should have had that on to begin with. Let's see here. Only problem is, okay, let's see, I got to browse. Okay. Please bear with us if you're with us.
Hey, by the way, did you ever see that video I sent you of that sketch I wanted to do?
I think I did, and I was super busy. I forgot about that. It was that was the lab coat. That was why you have the lab coat, right? Something like that.
Yep.
Okay, this is let's see here. How do I do this? Well, you guys are just gonna probably have to get to see me with two heads for a minute till I can adjust the camera. I don't think there's any other way for me to do it. Yeah, that wasn't too bad. It just takes a second. There we go. Yeah, let's see here. That'll work. A little bit higher, maybe. So, you see the screen behind me on this laptop? Notice how it's flat?
That's funny.
Okay, but if you look at the path of the ISS, do you notice it never goes anywhere near the northern or southern region, polar region? Right?
Okay.
And all of us flat earthers already know why that is, right? Because you can't circumnavigate north to south because north is in the middle.
Mm-hmm.
So you can only go east to west. That's what the ISS does. If you take and see this yellow line on the screen, it's very thin metal or yellow line. If you take that and you put it on a flat map, just a circle. Now think about this. If the ISS is doing a circle, just like a plane is flying, circumnavigating the globe without doing a front flip. Whoops, there's my hand. I'm like, woo. But but really, if you think about it, the way that the scriptures put it, I got to tilt this down a little bit. The way the scriptures put it, heaven is where the birds fly, right? The firmament of heaven. And this darkness where we are is where Enoch said there was no birds and no water. And it was a waste and horrible place, he said. Well, if that's the case, there's no physics like we would expect there to be physics. So on Earth, we launch into what we think is an orbit, orbital velocity to orbit the Earth. And what we're doing is we're going just the right speed to fall over the fake curvature of the Earth. Now, if we think very carefully.
Just to stop you real quick, Deborium says he believes he has sent the email.
Oh, I'm sorry. I got me and my ISS talk again. I got to go and make sure that I send him the email. Sorry about that, Andrew. I'm not thinking. I'm working on this here. Okay, let's see. Sorry, guys. I can't believe my computer crashed yet, but it does crash all the time. Let's see here. Okay, yes, I got an email. Nice. Oh, it's Davey. Nice. And okay, all right. I'm gonna send a link. Let's see here. I'm gonna send a link to her because I don't know if she wants to pop in. If she does, that would be great. And I'm sending that right now. And then to Deborium. Inbox. All right, got the peace sign from Deborium channel. Try this link, Andrew. It should work, hopefully. My ISS head is probably not quite in place. Okay, message sent. All right, so that should put us good for that. All righty. So, Alan, what's new?
So I had kind of a thought while we were talking earlier.
All right.
And I don't really know if it's something that I feel like dealing with, but what do you think of the idea of like trying to do like a GoFundMe fundraiser to raise a pool to make available for the website challenge? So I was thinking maybe there might be a bunch of other flat earthers that want it. What's that?
You mean to up the ante or whatever?
Yeah, it would just be. I'm curious to see how big it would get. You know.
Well, and what's interesting is about that is the bigger that it is, probably the more chance that it would be where someone would say, "Oh, I'm gonna," I did it like with the Zen Garcia thing. Hey, Deborium's in here. What's up, bro?
All right.
Is audio working?
All good.
Audio is working. I can hear you. All right, Andrew, this is Alan Spencer. And Alan, this is Andrew DeBoer. And Andrew's a good dude. But we disagree on a lot of things, but that's just fine.
Yeah.
So, how's Andrew doing?
Pretty good. I just got off work. Excited to see your stuff.
That's what I figured. That's what I figured. We kind of ended up doing it right away, and then I was like, well, we'll see. We can always do it again if he doesn't show up. But I'm glad you. All right, I'm moving this a little bit. Glad you showed up. So yeah, you should maybe. What do you want to talk about, or what do you want to chat about?
Well, I'll go ahead and start.
Go ahead.
Oh, go ahead. Go ahead, DeBoer.
Well, a common thing that you guys love to discuss about is gravity. So you want to go there?
Well, actually, if you don't mind, I was going to start with your. Joe sent me kind of what you guys were talking about. I guess this was yesterday, or maybe it was earlier. You were talking about how we've sent probes to Jupiter, and Jupiter's thousands of times farther away than the moon. And you guys were talking something about phases or something, but I'm just kind of curious. When you say the word "we," who are you referring to?
Well, us as in humanity, because it's a great achievement. But I'm guessing you include yourself with that.
Well, yeah. If you're using the word "we," then we haven't sent anything to Jupiter. I mean, and the reason I ask this is just because if we're going to have a sincere conversation about breaking down the truth, we need to use the right words in our communication. So, if I may, what you actually mean is they have sent probes to Jupiter, right?
Well, they as in
NASA,
yeah,
or
NASA.
whatever agency you're talking about.
Yeah.
Okay. So then the next question that comes up is, do you have access to any of this data?
Yeah, it's all public.
Well, I'm not talking about what they publish on an article on a website. I mean, do you literally have access? Can you walk into NASA and start saying, I'm going to take a look around at your data?
Well, of course not, because the equipment's extremely expensive.
Right. So scientifically, this raises an unfortunate giant red flag, which is when you say they have done this. If you're making that claim that NASA has done this, but we don't have the access to their data to verify it, then that means if this was a court of law, we couldn't use that as evidence. We have to have something else. And so that's just one big issue. I mean, the claim is, at least my claim is, they haven't sent anything to Jupiter unless someone brings me the actual data that shows it. Because anything that they put on a in an article on a website, quite frankly, could be done by my 12-year-old nephew. He could just make up a website and write down the same stuff, and there wouldn't be any way for any of us to know. And so the next question would be is, if you, maybe it might be easier, let's just do the sun, since the sun is reportedly much closer. So how far away is the sun?
Approximately 93 million miles away.
All right. And how was this verified? What was the experiment that was done?
You can use Kepler's third law with the parallax of, I believe, Mars, and you can mathematically work out the distance to the sun.
This was the experiment, is what you're saying?
Yeah.
That they did? Can you show us?
You know what? Can I give some info? I mean, it's probably not adding too much, but I don't think that we should use any of the planets, we'll call them, to, I guess, the planets don't do what all the other stars do. They have their own weird courses. They go like on weird thing. All the other stars do something different. So it's almost like we have two things going on in the sky. That's about all I wanted to add. Sorry, I don't want to cut you guys you keep going.
Yeah, well, that's perfect, as in because they're planets. They're a lot closer, and they're not stars. So that's why they would take different orbital paths, and you could actually see them different movements in the sky.
Well, they
So-
just, yeah. Okay.
So what was the experiment that was done that proved the sun was 93 million miles away?
I don't recollect who actually done it. Many people actually tried to do it in the past, and they were off by quite a bit, but they kept getting closer and closer down. And then I believe Kepler came along and did a whole bunch of celestial observations, and they did really great mathematics on that. And then with the third law of the orbit, then you can mathematically calculate to the sun using the parallax, and that would work mathematically.
So it's all just concept, though, as far as
Yeah, there's no experiments happening.
well,
No
I
measuring.
I understand where, the idea of we can look and we can look at orbital movements and patterns and things, and we can make assumptions. We can make assumptions that do make some sense, but is there anything we can actually do to verify or not verify even, but to get these ideas? Like, I mean, when I look up at the sky and I see, just an example is a great one, because Andrew was watching Jupiter along with when I was doing the live stream yesterday. And it's kind of cool because I'm looking at what I'm reading in the scriptures about is a prison in the host of heaven. Jude talks about it. And then of course Enoch and a lot of these other books, but in the Bible, Peter, 2 Peter 2 verse 4 says it's basically calling where the planets are, it's calling them hell, or it's calling that place hell. And so I've in the past I've understood hell would be underneath us, but hell's actually at the bottom of heaven. And then in Genesis, it says that the darkness was over the face of the deep, and then God said, "Let there be light," and all that. So there is a story there, and these angels are, they in the end they end up defiling mankind and leading them astray into sacrificing to demons as gods. I think that's talking about the planets. But I'm sorry, I probably got way off on that. You guys keep talking. I'm going to zip my lip for a minute.
Yeah.
You're
The
good,
reason
man.
I bring up the question is, let me see if I can show it on my computer here. Well, I'll just do it this way. If you're standing in a field and there's two airplanes far off in the distance, and one's closer to you and one's further away, and you're kind of seeing, something happen. Kind of, I'll see if I can do this with my fingers. Kind of like this. And the one that's closer to you, and there's one that's farther away. You can do all kinds of mathematics and show, how fast they're going or how big they are or whatnot, but none of it means anything unless you can verify that they're actually the distances you assume, and that they're going the speeds you assume, because using math just on, kind of on an elementary level, just with proportions, you can get a million different answers with all of the, the correct usage of the mathematical formulas. Do you know what I mean?
Yeah, but the problem you have there, so you're saying is it's just an assumption because we haven't actually taken a measuring tape to the object.
Yes, or whatever technology you're using to determine how far away it is, we are not given the option to check. No one has this magic tool that you can point at the sun and shows up on the screen saying 93 million miles.
Well,
Except,
yeah, there's not. You can do this mathematics yourself.
But it's just like let me just add one word to the conversation: tangible, something tangible.
yeah, I'm aware I can do the mathematics. That my claim is the mathematics can give you many different answers, just on changing the assumptions. You ultimately, if we're talking about this experiment with the two planes going by, at one point you must find out at least where one of them is, how far it is. You have to literally measure it out, or you have to have someone inside the cockpit, verifying how fast it's going, or whatever variable you're going to use as as your kind of like your home base concrete variable. That one has to be verified in some fashion. And just using a bunch of math is nice, but it doesn't get you the actual answer.
Well, the thing is, you're incorrect on that point. You don't need to, as in, for you to do these calculations, you need two observers at a very far distance apart from each other, and then you use that distance, that certain distance that you know for 100% certainty, and that would be your concrete stuff, and then you could use the rest of the mathematics and work it out from there.
Well, let's see it.
Want me to do it now? I mean, I don't
Yeah.
have the equations memorized at the moment.
Is that over a curved surface or a flat surface? The distance. That would make a big difference.
Yeah, you once you take in, because you have to do the curvature of the Earth on that stuff. Because I was gonna actually attempt to do this with the moon, but
that's a problem when there's no curvature of the Earth that in any way that we can measure in any way. So what I'm saying is, if two people are distance apart, if the Earth is curved, like with the shadow and stick experiment, you're going to get to a much further away point than if the Earth is flat. You're going to have a close, you know what I'm saying?
Yeah.
So the math can be, let me give an example that I heard on, I got to plug Authentic Intent, Joshua Swift, his channel. I love what he's doing lately. He's hanging out at, I think, Lake Calhoun, and he just set up a table there, and he's just having conversations with people, and it's quite entertaining. But I heard, and I apologize, I don't remember her name, but someone that hangs out with him down there doing, speaking to people and things. She said an example she used was, okay, let's just say, hypothetically, I have $2 million, and a simple math question. Tomorrow I'm going to spend $1 million. So the simple answer for how much money I'll have the next day is $1 million, right?
Correct.
But I don't have $1 million. So the math worked, but I don't have $1 million. I never had 2 million either. So you know what I'm saying? It works for the concept of the story, and it does work. Like, we can do all the numbers and we can do the formulas, and they do work. But there's so many things that seem to be assumed, like distances to things. And I mean, even that, like, like the Jupiter, going back to that, the moon's going around Jupiter. I believe that, well, I don't have any scriptural reason to believe this other than kind of the story of what that place is. But I think that those are probably surrounding it, keeping it from transgressing, like under chains, because that's what Jude said, that the wandering stars are under chains in reserved for in the blackness of darkness forever. So I'm thinking, that could be just like guards. Do you know what I'm saying? You have to kind of be thinking on the way that I'm trying to present it, that they're luminaries and that they're fallen angels taking those forms strictly to defile mankind at the end. So that gets that back to the beliefs. But you guys, I'm sorry, I keep going. You guys keep going.
You're good, bro.
Yeah. Here's another good way to put it. I mean, water boils at what?
At 100 degrees Celsius.
At sea level.
Pressure.
Very good. And that's one of the times that we actually can say the words, we know this, because all three of us, if we had to, could set up a pot right here behind us and boil water and measure it, with a thermometer.
Kind of like the cold moonlight. Had to throw that in there.
Very good.
Yeah, there's a lot wrong with that.
There is, but there's also one thing that about the cold moonlight thing. Let's forget about temperature, forget about everything, because we're looking with the infrared heat gun, right? But here's the important thing. Why does the infrared heat gun measure a higher temperature when you're measuring the shaded areas than when you're in the direct moonlight? It measures a colder temperature consistently. That's what I would say. So I'm not saying that the moon puts off a cold light as a fact, or we don't have proof of that, but we do have a way to measure the temperature of the said shadow and shade.
Okay, so with that, it's all about the thermal radiation of the object itself. So it doesn't matter if it's in an empty room or not. If there's a wall next to the object,
Mhm.
or the ground you're trying to do, it's thermal radiation, which comes off in infrared light, bounces off the walls and comes back to it, so it'd keep it a little bit warmer than things that were not.
So in the experiment, how does it measure the colder temperature consistently in the moonlight side of this experiment?
Well, if you set it up in a certain way, well, not in a certain way, without the actual immediate boundaries right next to the object, because most
Yeah,
people,
you have to do it very, very carefully. Just like, I mean, you can't just, I have boulders in my yard that have a shadow of the moon on one side, and they have a that doesn't shaded on the other side. That doesn't work because we're talking about a boulder that's got heat from the sun, and it has to be something that is not affected by any outside wind or anything, unless they're both affected equally together.
correct.
So we're setting it up. We're setting these things up very carefully. I mean, it's not like I just say, yeah, I want to believe this, so I'm gonna just say, yeah, look at that worked. No, you have to be very careful doing it, and you have to get it up off the ground. You can't have, like, even your thing that's going to be making the shadow can't be anywhere near the experiment, or you're going to be getting. So I agree with you, Andrew, on that, but I just wanted to articulate that we do these things very carefully. So,
Well, also one of the reasons why it is nearly impossible for there to be cold light. Cold light is only theoretical at this point in our current understanding of physics as an hour of mankind, because a light wave has energy, correct?
it's
We don't know.
light. I don't really know. I mean, they say photons, but there's no particle. There's nothing of mass.
It's a particle and a wave at the same time. It's a little finicky right there.
That's because it has to be, Andrew. That's what I'm saying. You can't have a medium out in space, so they have to have a photon so that the light can get here. It's like something made up.
But it's not. Have you heard of the double slit experiment?
Yeah.
Yeah.
That's just the smallest amount of light that a person could measure. Like at a certain point, the light is just not enough for our eyes or anything to pick it up. That would be what a photon is the least amount of light that we can measure. So it's not an actual thing you could hold in your hand.
Yeah, it's energy, so you wouldn't physically be able to hold it. But my point is, light carries energy, so if it interacts with anything else that's, say, colder than it, it's going to bounce off of it, transmitting some energy to that object,
Sure.
which will result in heating it up. So there's no possible way light can have a cooling effect.
Oh, you're saying like the friction of it, or because
friction,
reflection?
Yeah,
or
reflection, because it
reflection.
Some of its energy onto the medium.
If it's heat energy, right?
Well, it doesn't really matter.
Well, if you have a dry ice and you put your hand really close to dry ice, your hand will get cold. You don't have to touch the dry ice, and it's because there's a medium that temperature, the cold is literally coming off of the dry ice, and your hand, it radiates to your hand. So that's exactly what we'd be talking about here.
Well, that's a bit different. That's the air molecules actually colliding with the ice and transferring it,
yes,
energy of the molecules moving.
And so I'm saying that the moon is right there doing that too.
So
Yeah,
it's not out in a vacuum.
Do you know who Dr. Richard Feynman is?
I do not.
He's the foremost authority on quantum mechanics. And unlike most people, I actually poured through all of his. He's like one of the guys, says he was contemporaries with Einstein, worked on the atom bomb, one of those guys. And if you go on YouTube, you can check out all of his lectures. It's like, 50 or 60 hours of all of his actual lectures on quantum mechanics. And the guy himself says that he doesn't know what on earth light is, and he knows that no one else knows what it is. So it's kind of it's a bold claim to start saying that we know what light is and what it's doing. My claim is that no one knows what the heck it is, and it's really quite a mystery. And so to say that light, there's no way that light can have a cooling effect, I'm saying that there's no way you or I could know that, because the foremost authority on quantum mechanics says that no one knows. And through all the hours and hours, thousands of hours that they did in the labs, he says it's a great mystery. We don't have a clue what's going on.
Yeah, that's an argument of authority, but the point
No,
here.
well, I only brought it up because what I've noticed is people bring up the double slit experiment and they talk about quantum mechanics and stuff, and then they never actually went through all the lectures from the guy who wrote all this stuff about quantum mechanics. And so, yeah, I mean, it's I'm not trying to appeal to authority. I'm trying to say that most people are making these claims about light, and they haven't looked into it enough to know that not only do they not know a lot about it, but they don't know that no one can know about it. It's just way too complex and mysterious.
Yeah, that's correct. It is extremely complicated, but the thing is, we know a certain amount about it. Light does carry energy, but we know this because you can go at higher frequencies, and it will literally microwave an object. There's microwaves.
Sure.
So we know it carries energy, because if it did not have energy, it would not move.
No,
right, but
what's energy?
That we know light.
I mean,
that we know light has energy doesn't mean
anything.
Anything.
Light is light. It you can have a flashlight with a beam, and you can beam light towards something and make it light up. I guess what I mean is if there's heat that travels in light, and I'm not saying that, like, I think you're right, Andrew, that we would say that it's theoretical, or at this point it would be theoretical for us to. I mean, it would actually be not right for us to say we know that that cool light travels through the. I don't think we're trying to get that technical. I think I'm just saying that you can measure the two different, the shade and the light. You can measure them, and then people say, well, you're measuring something else. Well, whatever we're measuring, it's the moon, and I don't know how far away it is. I don't know what it's made out of or where any of it, but we do know that it consistently gives us a cooler temperature when we measure the temperature of all these, and we can do it in so many different ways too. But
then why, when I look at other people do it, when they set it up in a certain way where there's no walls next to the device being measured, you don't get a temperature disparity.
You don't get it all the time. You don't.
So it's not consistent.
It's not consistent.
Or there are factors in the experiment that haven't been accounted for.
The atmosphere too. You got to think about, like, the temperature of the air and the humidity that it's going down through to get to where we would be able to tell a difference. I guess what I mean is, if I take one of the, I'm not saying I know about these guns or these temperature guns and stuff, but I do have one. I actually have two, and I've taken and I've done some pretty, far, I'd say farther than a guy would normally go, experiments with them, like boiling a thing of water in a glass pan or a metal pan, and seeing the reflection, trying different surface textures of things, and noticing that it doesn't seem to make too much of a difference. And sometimes it's when you can measure it, it's a couple degrees consistently, and you only have to be moving But like I said before, you have to be careful that your experiment isn't being affected by, you're having the sun go down and the moon come up when you're trying to do it, because the moon, you're going to try to do it when there's a full moon. And so at the full moon rise, the sun is setting. Every full moon that's how it is. So I guess what I mean is there's a lot of variables that need to be considered, but it consistently gives it consistently is colder. Yeah, on the temperature readout on the gun. I have to be very, because I don't know what's happening in the gun, I don't know enough about it, but just that it changes consistently, or that it measures consistently, is interesting.
Yeah, and I gave a reason for that, in being the thermal radiation off of the object. That's why it wouldn't be. It's not consistent within the other people's channels where they've taken that same exact experiment and they've done it purposefully, trying to avoid any type of thing that the thermal radiation could bounce off and go back into the object.
Mm-hmm. I guess, yeah, that's something that here's a point that's kind of an important one for all of us. And I think we'll all agree on this, that no matter what, like, let's just use that moon for the example. What if the moon was putting off cold light and it was getting down to the earth and we were measuring it? We're like, wow, we're measuring cold light somehow. And so there's some kind of cold light that we don't know about. Okay, let's just say that's the story. Then what that would mean is that I believed something that was right and Andrew believed something that was wrong. If it was the other way, and we're just thinking we're measuring cold light, or we're measuring something cold, and it's actually an obvious problem that we're not seeing with the gun or with how we're measuring it or whatever, and Andrew's right, then Andrew's right about what he believed, and I'm wrong about what I believed. Do you get what I'm saying? It's a belief for both of us. That's the point I want to make. It's fake.
I wouldn't call it a belief.
Well, I don't believe what you think is. I guess when I can measure cooler temperatures in the moon, you know what I'm saying? So I guess what I'm saying is, if you believe water's curved and I believe it's not curved, I have evidence that I believe and you have evidence that you believe, right?
Sure.
I'm just saying I can take you up to Mille Lacs and we can look further than we should be able to see over that curvature. I'm just saying it's very little, but it's something that all around the world, in every country now, people have been doing consistently for 3 years, pointing out how much further we can see than would be possible. So maybe Mille Lacs is a small lake. It's not quite big enough to make a real solid, decision or, get understanding. And well, then we just go and we look at a bigger lake, or we look at, there's lots of channels that are out doing that kind of stuff. So,
yeah.
A better way to put it might be, Deborium, have you personally done the double slit experiment?
No, but have you personally done the double slit experiment?
Nope.
Well, no, but I'm the one who's saying that it's nonsense. So the reason I ask is, do you know anyone else who has personally done the experiment and had you present while you were doing it?
I got to put a shout out there to Deborium channel. He did an experiment. What's it called?
Cavendish experiment.
Cavendish experiment. And of course, I think it was a great, you should check it out when we're done or whatever. Go to his channel and watch it. He did a great video and he did a very good experiment or whatever you want to call it. Would that be an experiment or a demonstration or whatever you'd call it? And I thought it was really good, but the conclusion is just different is all. So I think, and he went to long lengths to do this, Alan. You have to check it out. We're talking about melting down lead and everything, right?
Yeah, I had 30 pounds of spare lead and I put that to use.
Spare lead, I like that. No, I think that was great, Andrew.
Yeah, well, back to the whole, that type of argument doesn't mean anything because you're trying to say if I wasn't there, it's not true. What is that? How is that?
No, that's not what I'm trying to say. What I'm trying to say is, well, first find out let's find out a few more answers. So, do you know anyone that has done the experiment personally that made you privy to it, that you were present for?
I would no.
Okay. I find that's the case for everyone. And me particularly as a teacher, I know that I work with a lot of other teachers, and the vast majority of teachers are spending each year just kind of going through the motions of a curriculum that's passed down to them. And I know, at least with all of the science teachers that I've worked with, and I am quite confident when I say that all the other science teachers, especially in public education, are most likely never did their own personal experiments, at least in their own studies, at least not an experiment that wasn't done already. Like, I'm not talking about a science teacher who went to school to become a science teacher. So they do a bunch of other experiments that they learned in school that have already been done. Like, I'm saying their own personal study, their own personal experiments, very, very, very few science teachers have ever actually done on their own.
Well, of course, they're teachers, not the scientists, because the scientists are the ones doing this groundbreaking research about the double slit experiment. You can go and read the paper.
Right, but I'm saying I don't want to see a paper. I want to see the actual thing. I want to find one person on this planet that can show me the actual experiment happening with all of the instruments, and we can able to take apart the instruments and use them just in the same way as if we had to boil some water. You know, that's the whole point. Is like, is there's one person on the earth that can show me how to boil water? We all say yeah, but double slit experiment, it's not the case. It's usually in some $50 million lab that none of us have access to. And
Yeah,
just because they write up a paper and, put out an article doesn't mean diddly. I mean, it might all be true, but scientifically it doesn't mean anything if we can't verify it.
it was
That's all that I was saying.
repeated independently.
By who?
I don't recollect the correct names, but you can't just
No one knows.
I think it's more of a concept. Like I think Alan's not trying to be like necessarily only specific to this light experiment. This
Right.
is the general thing we see everywhere. And when we try to do these experiments, we find that their results are often only assumed. That's the best I can give it, is assumed. So, and I'm not saying that there's no credibility to any of these things, but like an example is a long time ago, I was talking to my brother about light or whatever and photons or something. And what it came down to was I was saying, well, I want to see a photon. Like, let's measure the light and measure what I want to see how this is done. Well, you got to have equipment to do that. And I'm like, well, okay, well, let's go get the equipment. Well, we can't afford it. Okay. And I said, well, how are we going to do it then? Well, they already did it. And I said, well, what are we measuring? Because you can't hold it in your hand. I mean, I have an LED light right here and it's shining. It's not, again, it's not tangible in the air. I mean, it's light or it's, I guess, a photon. And then so I say, well, how big is a photon? Well, it's really small. How do you measure it? Well, a photon is simply the smallest amount of light that we can detect. It's not a particle or I mean, this is just my take on it. So I guess what I would say is that I don't give those kind of experiments or whatever we want to call them, claims, I don't give them any credibility at all, because there is nothing that anyone can produce that is actually verifiable. Like and like you said, Andrew, I give you credit. You said that it's been reproduced or whatever, but I think what we have is 12 disciples or 12 prophets that went to the moon. And then we have 12 disciples that preached the gospel. I really think that it's like a competition in between those two camps. That the in the Bible, of course, I'm going to go back to the Bible, but in there, it's told that we have no excuse because of our surroundings that we do live in, because of all these things that we're studying, light and photons and all these things, this amazing nature. That's why we have no excuse. Because when we look at that stuff, we should be saying, I mean, like an example would be clouds. If I say, how come the clouds, if we're talking about gravity, how come the clouds can sit up in the air? And there's a scientific answer. But what I'm saying is there's a scientific answer that goes completely against your theory of gravity. I don't care if it's collected in particles to big enough to be a drip. The water's up there, right, in the cloud. So I'm just saying there's lots of things like that you can look at it with the scientific answer, but that doesn't explain what's actually happening. The wind, it blows because heat rises, and we know a lot about it, but we don't know what makes the wind. Well, it says in the scriptures, but I'm just saying there's a material physical way to understand things, and if we limit ourselves to that, I think we're going to be missing out on the actual truth. That's my take.
If I can go back and mention, like when you say, well, it's been reproduced and it's been done by such and such people that we don't know, like even if it has been reproduced and it's been done by other people, the next question is, of course, well, can we check? Like, can we just go in that lab, especially if we own the lab, like in public universities and stuff? And the reason why that was such a big killer for me is because when it comes to things like the high altitude weather balloons and the super zoom cameras and all that, we're the first generation ever in human history that just decided to check and find out if all the stuff that we're being told is true. So we sent up some weather balloons and it looks really flat, and we zoom a camera in over the water and we can see all kinds of stuff that we shouldn't be able to see. Until the last few years, we really didn't have that capability. And so I just want to use the same standard against all this other science that we're being told, like the double slit experiment and so on and so forth.
Yeah, well, actually, with the double slit experiment, with about 3 seconds of looking into it about the replication, you can do it yourself at home.
Oh, okay.
All right, let's do it.
Yeah, I'd be interested in actually doing it. I'm not kidding.
Yeah, I'm gonna look it up right
because
now.
that would be something else to see, I think.
3 seconds. Double
nice
slit
Whoops, how do I get
experiment.
back? There we go. I'm gonna mute myself for a minute.
Can everyone see my screen here?
Let's see here. Yep.
Okay, which one should I click on?
Let's see here. Well,
Because I can guarantee you these three won't have anything of value.
You can guarantee. I put replicated at the end, and you can actually. Let's see here. Which one did I?
Replicated. All right, where should I go?
Actually, let's see here. Down a little bit.
Hey, do you guys know on Hangouts, if I click on the icon for Alan, I think it'll keep his screen, but I don't want to try it because what if it like hangs up on him or something?
A little bit.
Sorry, say it again.
It was a little farther down here. Let me see the exact. It's quantum mechanic. Is it possible to produce a double slit?
Okay, this is a message board.
Correct.
Okay, now what?
Read it.
There, I got you up there now, Alan, your page.
You want me to read all this?
Well, actually, if you were...
I just want to watch it on YouTube. No, I'm just kidding.
But I mean,
there-
essentially, that is it. I want to see the person that actually does the experiment.
Let's do this. I think that we all three of us and probably everyone watching understands the point being made. And I think that Andrew has a good point saying that this is an experiment that other people have done and whatever. And then Alan has a good point saying, then let's see the demonstration or the experiment. But as far as like, that's a double slit experiment. That's pretty crazy to think that it's going to like really teach us much, right? If we know, if like we know a particle of light or a wave or a both or whatever, but that doesn't really need, for me, that's like a topic definitely of like learning and stuff. But if we were to go to the basics, like the basics of why any of that would be studied at all, it would probably be like the sun and moon. The sun and moon, the only reason why we're studying light and hope, science is hoping that they can figure out some way to call it a particle or whatever, and that moves through a no medium, because they have to, because they need that sun to be at that distance in order for the heliocentric model to continue on, right?
Well, and a lot of stuff on the double slit experiment might be true. I mean, the whole point that you have this interference pattern sometimes, and sometimes you have the column pattern and stuff. Like, I'm not disputing any of that. I'm sure all that is happening. I'm just saying that what they're claiming and all those assumptions now that they're making, I think, is what Joe was talking about. And when it all comes down to it, the guy that basically founded it, Richard Feynman, when he was done with all of his lectures and basically said, we don't know what the hell we're doing. Like, we don't have a clue what we're studying. Like, it's all just a big mystery. And so that's what bothers me.
What's amazing about it is you find new stuff about it all the time. That's why it's studied.
Yeah, all the more reason that it's a bad idea to say that we know that light doesn't have a cooling effect, is because we're learning more and more about it every day.
With the laws of thermodynamics, it is impossible for it to cool.
But there's been issues that have come up that kind of throw the laws of thermodynamics out of the window.
If we're talking about the laws of thermodynamics, we need to talk about how the a weak vacuum can outdo gravity anywhere, and it does all the time. So, like, well, if you just take a simple vacuum chamber.
And I'm sorry, y'all, I got to head out. I've been on this stream for a while, but hopefully we'll get a chance to continue on later.
Yeah, for sure. Thank you for hanging, Alan.
Yeah.
We'll have to do this again when we have better, that was my fault, my computer and all that. So
all good.
It was great.
See you guys again. Take care.
Have a good one, man.
Yeah.
Thanks. Awesome. Alan's such a cool dude.
Yeah.
So yeah, Andrew, I definitely understand where you're coming from. I do, because I've been there. I have to admit, I haven't been there with interest until the last few years. I mean, you're young and like you have a natural interest in these subjects, obviously. I don't know what the good word would be. Like you have a scientific mind, clearly. So, and then like the things that you're talking about, I'm not going to argue with something that I, don't have an opinion on because I don't have any experience in or something like that. So like when you're talking about like this double slit experiment and stuff, I don't know what they find. I don't know. I've seen the basic idea, but what I'm saying is that I haven't done the research that you've done on this subject, but I still have a hard time giving it much veracity. Not your part of it. I'm saying just the idea that we're going to know something a lot about light. It's a hard thing to we can make a lot of claims, but it's hard to prove them. Do you know what I'm saying?
Yeah, but that's why we have all this science backing up. All the evidence points to it being a particle and a wave at the same time. It's not saying it is
Both. Or
that. It could be either or
you're
something.
saying it works
And
through it works in both, is what you're saying.
Well, it behaves like both.
Behaves like both. That's a better way to put it.
And yeah, it's not I'm not saying it's exactly a particle and a wave at the same time. It exhibits both characteristics of it being
Yep.
that.
Yeah.
That's what the
And
double
why actually let's talk about that. Let's talk about those two characteristics that it's what's the right word? Not displaying, but it's you get me. But those two things, what are they?
what do you mean?
Well, it's I'm trying to word it right. It like there's the light, like what we would call a photon, right? So that would be like the particle thing that we're talking about of it, but it's moving as a wave, right?
Yep.
And but it can move through a vacuum, right?
Yeah.
So that's kind of like where again, the physics that we have on the earth, it could be said that when you leave the atmosphere, those physics don't necessarily apply anymore, right? I'm saying if the sun's 93 million miles away, maybe light just is automatic through that vacuum of space, and then only in the atmosphere is any of the stuff, you know what I'm saying? There is any of the heat felt or any of the photons measured.
Well, that would be true because there's nothing for the particles to interact with.
That's what I'm saying. That gets back to something tangible is really hard, or something not tangible is really hard to measure. I don't like if you have a tape measure, you have to push it up against something to get a measurement. You know, you're not just guessing at where, you know, you send your tape out 15 feet in the air and you say, well, that's about where that is. And I mean that you get what I'm saying there, don't you?
Yeah, that would get into relativity a bit too, which is
and orbital mechanics too.
Yep.
So there's a lot you can learn from that. But what I'm saying is, oh, actually, you know what? Something that we talked about briefly last night, kind of through the chat, is the crescent that we see on Venus and the crescent that we see on the moon, like that, those phases.
Yep.
Not existing on Mars or Jupiter. And I guess that's the only two that Saturn, I guess.
Why do you think we can't?
Well, because I have a different idea of what those phases are from. I believe that those phases are, they are from the sun, but it's not because light from the sun. Oh, that was it. That was the thing that maybe I think maybe you were misunderstanding something. And we should actually talk about it really quick. The shadow, or I can't call it a shadow, but the non-lit part of the moon, during the waxing and waning, the non-lit part of the moon, the black part, that's not a shadow. That's just not in the light, right?
Yeah, well, it's casting a shadow on itself.
On itself, yeah. That okay? I see. It's the backside of the sphere from the light.
Yeah,
there's only one light.
The reason.
So what I'm saying. Oh, go ahead.
The reason why you can't see all the planets that you've mentioned are ahead of us. Well, not ahead. They're closer to the sun than we are. That is why we can see the crescent
in the sky in the south. That's just where they are for, like, when I look at them.
Well, yeah, I guess if you look at it that way, but in the heliocentric model,
yearly cycle, maybe like that.
I won't go that far.
Okay.
But yeah, in the heliocentric model, their orbits are closer to the sun than we are, so we can see the back sides of them. But whereas Saturn,
wait a minute, all right, I don't think that's true, is it? Earth is the third planet from the sun, right? There's Mercury and Venus,
correct?
And then Earth, so they're further from the sun, right?
They're closer.
I'm saying if our orbit was third from the sun, and the fourth would be farther from the sun, which would be, what would that be, Mars?
Yeah.
And then the fifth from the sun would be Saturn, I'm assuming.
Yes.
Or Saturn further away.
Saturn. I think it's
I
Saturn.
think Saturn's further away than Jupiter. I can't remember though. But what I'm getting at is those are further away, right?
Yep.
So okay, continue. I'm sorry.
Yeah, since they're further away, we won't see their backside. So how would we impossibly see the crescent?
Well, because if you look up at the sky, like tonight, I'm not sure where Jupiter will be. But what I'm getting at is we have a full moon tonight, basically. But a week ago, I was saying how we had about a half of a moon, and it's nearly in the same spot in the sky as Jupiter. What I'm saying is that the sun is in the same, like, it would be hard to demonstrate it, but the sun is in one spot and the moon is in this spot, and Jupiter's in this spot, and the earth is in this spot. Earth is only getting one angle. The sun is only getting one angle. Do you get what I'm saying? So the light's only shining from one angle, and it is only being viewed from one angle. So the crescent should be on any object that is beyond the, well, if the sun is behind us, or whatever you want it, behind us, hard to say. Do you get what I'm saying? Like if we had just a flashlight and we point at anything in the room, it's going to have that dark side. And if Earth is in one spot and the light's coming from that same angle, and there's two things in the same or close to the same spot in the sky, slightly different angles. But what I'm saying is that a half moon, what's keeping that, the part that's lit up on Jupiter, which is the whole thing, what's keeping the part of the moon not lit? That's what I'm saying.
Well, you're thinking about it more in two-dimensional. It's vast distances and at very different, I don't know, relative to us, it would be at
but apparent angles. Like if you have like one camera, you just put it one spot, you get, you know what I'm saying? Like if you stop everything from movement and everything, and you just imagine just for, do you know what I'm saying?
Yeah.
So I think it's hard for me to picture that, I guess.
Yeah, well, there wouldn't be any conflict in why the one night where you would see the crescent on the moon and you wouldn't see any crescent on Jupiter is because their locations are completely different in the orbits around the sun.
But in the apparent position in my sky, the sun is coming from the same angle at both of them.
Keyword apparent.
Well, what I'm saying is it's apparent. It's there's a straight line between my eyes and the moon. And right next to that, that's almost that same straight line is to Jupiter. If the sun is in one spot, the sun would have to be on the other side of Jupiter in order for us to see any kind of crescent, or at Jupiter or further. Do you know what I'm saying?
Yeah, that's exactly why you won't see a crescent.
But the sun's the opposite way. It's not on the other side.
That's why we don't see a crescent.
Okay. That's maybe I need to look into that a little bit, or maybe I need to perform a parent experiment, like a shine a flashlight and take two things and put them somewhat to scale and see what happens.
Yeah, I want to get into making simulations through that stuff on the computer, so that I'm able to simulate that stuff.
Like with like rendering software.
Yeah.
Yeah, my brother writes software like that to deal with light and shadows and different textures and all that. It's really complex stuff. He's actually going to be releasing some software sometime here. He's been working on for like a year or so.
Yeah, it's really neat stuff. In the in that sense, recently there's a new thing called ray tracing, where they in real time in game or video or whatever you're doing, they simulate light, which is really hard on any type of computer.
Oh yeah, it takes a lot of. I
Yeah,
think I'm just trying to think of some of the names of some of the stuff that he mentions. I don't get too much into it, but some of the renders that they do, you can't tell the difference. Your eyes can't tell the difference. I mean, it's really good.
yeah,
And it's
he's amazing.
like they'll have like a sphere or something, and then he'll pick a texture, and then you can see how the light reacts differently. And I mean, think of light reflecting off of things so many times. Apparent position is so important when we're looking at anything in the sky. An example that is used a lot is the picture. You've seen it. We've all seen it, of a pink deck of clouds, a mountain in the distance, the sun just going down,
Yep.
and the shadow of that mountain up on the cloud.
Which is impossible on a flat Earth.
No, let me explain it to you, and you'll understand why there's nothing impossible there. First thing is, what is the why is the bottom of the cloud lit up? Is like, let's say if you're standing directly underneath and you look straight up, you'd see that same kind of pinkish color, right?
Yeah.
So what's lighting up the cloud, or is it just a reflection off of the water particles?
Well, refraction never goes up in that sense.
No, a reflection. I said a reflection.
Yeah, well,
simple reflection, like
a lake.
Well, like a mirror.
Yeah. Well, there's no body of water next to that mountain.
No, that's not what I'm saying. What I'm saying is, okay, let's take away the mountain and everything for now. Let's just talk about just when the clouds get lit up on the bottom side, or they appear to be pink, or like they appear to be lit up by the sun, right? Is that the actual cloud, the particles, the water particles or whatever, are they actually turning pink? We know they're not, right?
No, the light's being redshifted.
Okay, I guess maybe, okay, can you explain what redshifted is? Maybe I don't know what that is.
Well, the sky appears blue because that certain wavelength is able to pass through the atmosphere easier.
Mm-hmm.
And when the sun is setting, it has to go through much more
thicker atmosphere is what you're saying, right?
Yeah, and that will filter out the particles. Well, I shouldn't have said redshifting.
I think actually what you're saying is that the thicker the medium, because of that low angle, the sun, it's hitting so much more before, or the sun, is that what I'm saying? It's hitting so much more before it gets to your eyes.
Yeah.
Right. Or it has to go through so much thicker, and then as it goes up, it's gonna get thinner and thinner, and at zenith it'll be the clearest that you can get.
It'd be black then, because there'd be no scattering.
Yeah. Now, I guess what I'm saying is, if I have a mirror, let me just try to, I just want to make it kind of simple. Okay, I have a notebook, and it kind of gives a reflection where, let's see, can you see my face on it? You kind of see my face on it, right? No? Anyway, okay, there we go. The reflection there is the actual blue surface of this notepad. If I look from here, there's not going to be, well, especially when I move my face. No, I'm just kidding. There's not going to be that reflection to someone looking right here, right? So what I'm trying to say is that with the sun far off in the distance, out of my sight, right? I'm going back to that mountain shadow scenario.
Yep.
So let's just call me the observer, and I'm standing here. There's a mountain off in the distance to my right, and let's just say the sun is off to the distance just to the left of that. but I can't see it because the trees are covering it up, and I can just see the light coming from it or whatever. Like I can't see the actual source. But in any situation, that mountain, the angle of it's really simple geometry, because the sun is way higher than that mountain, right? We know that. It's way higher than that mountain.
Well, it wouldn't really be higher, it'd be more parallel with it.
Well, no, what I'm saying isn't I'm not going off of that we've fallen down the curve thing. That's kind of like, that could be another whole, argument or debate thing. What I'm trying to do is the simplicity of, let's take a flat surface, I guess. Okay. And let's just take a mirror and put it up above the flat surface, and take a light that is higher than the mirror. Let's just give some numbers. Let's put a mirror at 5 feet off the ground. So it's pointing down at the ground. So if you're laying on the ground, you'd see yourself in the mirror. Let's say that's at 5 feet. Now take a 10-foot street lamp, take that mirror and start rolling it away from that street lamp. The street lamp is always going to be higher than the mirror, but you'll be able to get a reflection from the ground to go to that mirror, to that light, once you're far enough away. Because as you go farther away, no matter what, that light drops down from, or we could say the other way, as the light moves away, it goes down in your view, from the observer's view, all the time, until it's going to go down until the trees are covering it up. Because at that angular resolution, the trees that are 5 miles from you are going to be they're going to be blocking that 10-foot sun. You know what I'm saying? So the geometry, it's like, how would I get a reflection if the sun's up here? How can I get a reflection off the bottom of the clouds if they're down here? All you have to do is move the sun further away, and that angle becomes available. Do you get what I'm saying?
Yeah.
So go ahead.
That's why the picture is so amazing. I'm assured that that's the picture that I brought up that one time.
I think I might have it on my, let me see if I can find it in my computer, and I can put it as my background possibly.
Well, there's clouds there.
Yep.
And there's no body of water for there to be reflection off of.
No, I'm not. The body of water I'm talking about reflecting off of is the cloud. The light is hitting the cloud and then coming to our eyes. That's what I'm saying.
So how'd the light get under the clouds in the first place?
Because the sun's under the clouds. Not literally, but from this observer's point, the sun is below the clouds. Because let's just take it right now. If let's just paint a picture in our mind. We're standing at the ocean. Or no, let's keep the water out of it. Okay, we're standing in a field, and the sun is just going down. Like we just filmed it going below the horizon, disappearing bottom side first. We just filmed that happen. And of course, there's some mountains and some hills off a couple states away that if it was a flat surface, no matter what, it would cover that up as the sun was going down. It would cover it up bottom side up, just like we see on an ocean or whatever. But that's kind of another subject. But as the sun goes down, like as we're just standing here, the sun goes down and we can't see it anymore, but we know where it's at. And so the curvature is what you're assuming, that the sun is actually going, or that we're going back this way, or that the sun's going down and hiding past the curvature, and it's able to still get that angle to the bottom of the cloud and bounce to us. I understand that, but what I'm saying is that same thing happens anytime the sun goes down, whether it's a curve or whether it's flat, because the sun, either way, it's still far away. Like whether it's 93 million or whether it's however far, 100 miles, it's still far away. And anything far enough away is going to disappear to an observer because the stuff between them is taller than the apparent position of the sun. I'm not saying the sun is actually going down. It just has to be moving away. Like if you would get what I'm saying about that, right?
Yeah, if it gets farther enough. Yeah, if it gets far enough away, then you would get the angle, is what you're saying.
It would meet that, where the ocean appears to meet the sky. It would meet that line and go into that line, that vanishing point or whatever we want to call that.
Well, the problem
Horizon.
Of the clouds, you can never get an angle like that.
You can.
You can't.
Well, how is it possible that I can take a picture with clouds above my head and let me do this right. Let me think. What I'm getting at is that if we're like you have to think of the perspective of something. Let me give an example. But see that it's hard because I know that you're going to kind of understand the example to be curvature automatically. So if it's curvature, I can understand what you're saying or where you're going to understand it. But I'm trying to get a different way of thinking, and we have to eliminate the curvature initially. I'm not saying we're going to say there's no curvature. Okay. I don't believe there's any curvature. I've seen the water and everything. But what I'm saying, that's not my argument. My argument is if my coffee cup here is above my head, that's not a good way to do it. I know what you're saying. You're saying, how can, like, if I was going to spit at the bottom of my coffee cup right now, how do I do that? That's kind of what we're looking at, right? If I'm the sun and I got to get my light to shine down at the bottom of my coffee cup, that's going to be kind of hard. But when we're talking about a reflection off of the bottom of my coffee cup, all I have to do is move out far enough or move my head out far enough away from the coffee cup, and it's going to be below. It's not physically below this, but as it goes further away, it gets, it happens every day. The sun goes down and it goes below the horizon or whatever we want to call it. The trees cover it up, or the waves on the ocean, or the distance. What I'm saying is it gets covered up. Maybe I'm getting sidetracked there.
No, that makes sense. But with the whole mug, in the picture, the light is angled up.
Yes, exactly.
So for there to be a light source, that to get an angle up, it would have to be below the clouds.
But
physically,
how come I can see it then?
What?
I know that the sun is above the clouds, but how is it that I can see the sun below the clouds? It's because we're talking about from one place. You know what I mean? We're talking about from an observing point on the earth.
Well, yeah. Well, the thing is, if you observe it, it makes perfect sense if it's a globe.
Well, to you, it used to me too. And I'm trying to point out that there's a different way to look at it is all,
If you,
oh, go ahead.
I don't know. It's impossible for you. Say you have a table, right?
I got a drawing here that I want to show you that will explain, I think. I forgot about it. It's right on my drywall board there, but I wanted to get the picture and show the picture if I could first, so we knew clearly what we were talking about. But go ahead, keep talking. I'm looking for the picture. So
if you can take a flashlight, right? And
hey,
I got it. There it is.
Yep.
So it's angled up.
Okay, but do you see the sun in this picture?
It's over.
Well, or where it is. I mean, you can kind of see the location of it.
Yep.
So that sun is lower than the top of that mountain from this observing point, right?
Yeah.
So my argument, or I guess I'm going to try to point you over here. Let me just try to get it. Oh boy, this might not be too good here, but there we go. Whoa, I drew that out a few days ago. I forgot I had it there. Okay, there we go. That you can kind of see it, right?
Yep.
Oops, I can get a little better. Sorry. Okay. So what I was trying to point out is that a person standing there, the sun is going to go lower than this person's head, right?
They would have to physically.
No, not physically. I'm saying you in this picture, let me go back to get that out of the way so you can see the other picture. And actually I'll get myself out of the way too. I think there we go. Well, hey, how's it going? So what I'm saying is in this picture, the light source is underneath the cloud deck. Like if we saw a cloud deck and then the cloud deck ended, the sun would be below the cloud deck. Not physically, but in the position that we're standing in for this image, right?
Sure.
So what I'm saying is that let's just say that over on the other side of the mountain there, we put a big giant spotlight sitting on the ground and it was pointing up towards the mountain. So that's why we get this up angle, right? So if there's a spotlight on the ground, we can see the light from it, but we can't see the spotlight necessarily. And we can see the angle that it's shooting off at this cloud. And we can see this perspective of the cloud, the shadow getting wider as it gets towards us. And so what I'm saying is that spotlight that we put on the ground would be bouncing off of those clouds and then down it. So it's a reflection of light because the clouds aren't actually turning pink. The clouds themselves are just still white clouds, and the sun going through all that low horizon or that low angle air is turning it kind of like that color or whatever. Do you know what I'm saying?
Yeah. So in order to get that, you need a light source below.
You sure? Because I think that this picture itself kind of shows us that ain't true because there's a shadow on the cloud.
Yeah, it works perfect because you're in your view looking at this, you know it's a flat plane. That's why in your head it works. You have to make it so the light has to behave all weird in ways that it doesn't.
No, it's not behaving in any weird ways. A reflection's a reflection. That's why I was saying picture the bottom of the cloud as a mirror, like a perfect mirror.
It's going to your eyes.
Or yes. What do you mean?
The light off the clouds is getting to your eyes.
Yes. Yeah. Yep.
But that doesn't prove any point. It just means the light source. For you to get an angle like that, the light source has to be below the clouds. The
apparent light source can, if it's far away, it's going to be the further away the light source. Oh, put it this way. Okay, I think I might have a way to explain what I'm saying. Okay, let's just say that this observer's position that is looking at this picture right now, let's just say that's on the east end of town or whatever. And so someone on the west end of town, they're not going to see this same, or they'll see the same type of shadow, but they're not going to see it in the same spot. They're going to see an entirely different thing if you move, like if you moved a mile away or something, right? I'm saying the shadow would show up on a different part of the cloud, or not the shadow. The angle would be different, right?
If you move positions.
Yeah, if I move positions, say a mile away from where this picture's taken. So what I'm saying is the sun, it changes. It's about in the same position, but the mountain isn't. Like if you move a mile away, the mountain has moved now. So if you move a mile to the right, you might be underneath this shadow, right?
Correct.
And then, so when you look up, you're seeing the shadow until you see that mountain, and then the mountain is blocking that brighter part of the sun that we're seeing right now.
Yep.
But you can still see all the pink around it. on the bottom of the clouds. And what I'm saying is that the bottom of the clouds is, well, we know it's not higher than the sun. So that if the, or let me get, turn this off. If the sun, well, we just have to look at reality again. Sorry, I'm fixing that. If we're looking at reality, me and Andrew, we're standing there and we're watching the sunset. And we watch the sunset, boom, it's gone. We can see the light from it still and everything, but it's gone. Is the sun in relation or relative to us or relative to our eyes, is the sun higher or lower than the clouds?
Well,
relative to our eyes, I'm just saying. Just play along. I'm not trying to.
it would be below the cloud.
Yeah, it would be below the cloud to us. So what I'm saying is that reflections work the same way as they always have. Nothing has changed about how light travels and how light works. What I'm saying is that I understand it to be just seeing the bottom of the cloud being lit up by that low sun.
So the light source is coming from below the clouds.
What's that?
So the light source is below the clouds.
Exactly. But not in physical, it's physically higher than the clouds, but it's far enough away where it's to the position we're standing in, it's below the clouds. Right? I mean, it's simple, but it's still at the same time kind of it's hard to say. It's hard to say that the sun being above the clouds could light up the bottom of the clouds.
It's
until you move it away. Then you can.
The angles would never point up.
That's not. I know what you're saying. Geometrically, the angles would not.
So then
the light's never going to go up like this, is what you're saying.
Which is happening in this photo.
No, it's not. Light isn't moving up at anything. It's a reflection off the bottom of, like if there's a mirror on the bottom of the clouds and you look up at the cloud, you're going to see down to the sun, right? But the sun is higher than the clouds. We know that. Maybe I'm losing you. I'd have to maybe do like a drawing or something.
The angles don't work for light to behave that way.
Well, but look at the picture. I guess what I'm saying is that even if you have a curved earth, like even if you figure you have the curvature, the sun, okay, take a spotlight. We don't have to have the sun. Okay, we keep this picture as being the sun, but let's do a hypothetical over here. And let's say, if we have a spotlight and we put it in St. Francis and we go to Anoka, and it's a really bright spotlight. Okay. We go to Anoka and we stand in Anoka, and the spotlight is actually on the ground in St. Francis. Okay. No, this doesn't work. The spotlight has to be higher than the clouds in order for me to make a hypothetical, right?
Yeah, and you'd never get an angle.
Well, but look at the picture behind us is proof that we get the angle. The angle's right here. The sun is lower than these pink clouds in the image.
The concentric model explains this perfect. You're using this as evidence for it to happen.
No. I'm not using evidence for this to be curved or flat or anything. What I'm telling you is that the bottom, okay, the reason why the shadow is at this angle and the reason why the bottom of the clouds is lit up isn't because the sun is physically lower than the clouds. That's what I'm trying to say.
It would have to be.
No. What happens to, okay, let's do the, we can like blow it up and we can exaggerate it. Okay, so if we're looking straight up, we're at 90 degrees. Okay.
Yep.
We go like this. So this is our line of sight changing, right?
Mm-hmm.
So at a certain line of sight, and it can't be at 0. It has to be before you get to 0. There's, what I'm saying is at that line of sight, that angle is so low, and your eye is, I guess what I'm saying is a reflection is different than, because these clouds are not turning pink, is what I'm saying. If the clouds were turning pink, like, it's just a reflection, just like, I'll try to do.
Yeah, well, what you're getting at is you're looking at it. Obviously, if you're on the ground and you're looking at the clouds, the light is going to your eyes.
Yeah.
We know that because you can see it. That's how that works. But for the shadow to be casted up like that, the angle of light has to be at an angle under and pointed up at the clouds, which is impossible to get if the light source is above it.
Okay, here's a light source. Okay.
Yep.
Here's a cloud deck. I know what you're saying. Let me reiterate what you're saying, is that this here is never going to get down here.
Exactly.
But that's not true, Andrew.
Bruh.
No, just wait, watch. What happens? Light's above it. Okay.
Yep.
And I can't probably demonstrate this with like accurate angles. But okay, so keep the light above this, but get it so far away that I can see. What I'm saying is I can see, maybe I can even do this. Okay, like if the light is higher than the notepad, obviously I can't do it. I can't stretch it out far enough. But what I'm saying is, if your eyes are seeing the light source beneath the clouds, then it's clearly possible for light to travel to the bottom of those clouds and to your eye, right? And I know it doesn't, like if you're going to draw it out on paper, it's going to be hard to understand that. But we're not talking about this actually being lit up. We're talking about the light going boom, boom, like coming from way back here, way far back here. It's lower than this notebook. I guess what I'm saying is, if I'm holding this like this, let me try to picture how to do this. Okay, if I'm holding this like this and a light is back on the wall, or you can't see my greens, you can't see my wall, but if a light is back there, and if your eyes are able to see the bottom of this and that light source, there's no reason why you're not going to be able to see that light off the bottom of this, bouncing off the bottom of this.
Okay, so let me reiterate what you just said.
Okay.
You said it's possible because of this, because look, you can see it happening right there. It's possible because it's happening. But what I'm saying is light doesn't behave that way because the earth is not flat, and it's because it's round.
Okay, no, but you're trying to think we're talking about flat earth, and that's not what we're talking about. This is simpler than that.
Yeah, geometry.
No, this is a simple observation that this picture shows right here, Andrew. What I'm trying to say is, in this image, is the light source lower than the clouds? Yes, right?
Yeah, the light source is physically below the clouds.
Don't say physically, because I'm talking about a picture. I'm talking about a single place that we're standing. We don't know where the light source is. We don't know if it's higher or low. We don't know any of that. What I'm saying is our eyes can see this or whatever, the light, the sun or the light source is lower than what's above our head. Like a jet airliner flying above your head at 30,000 feet. It just flies above your head. 4 minutes later, it's flying straight down straight down. Do you know what I'm saying? That is not, the plane has not changed its direction. It's flying in perfectly straight line still. But the person on the ground watching it for a few minutes sees it going down like this.
Yeah, the law of perspective.
Yeah, so as that plane is down, as you know, planes are small, so it's hard to see them that far away. But as that plane goes, it's 30,000 feet in the air, yet it's and I'm not talking about curved or flat Earth. I'm saying the plane itself is visible to my eye lower than the clouds that the plane is above.
It wouldn't be.
No, but it is.
Uh,
I have video on my channel. You can go out and watch anytime. Watch a plane flying away from you.
Yeah, it will approach the horizon.
Yeah, exactly.
Yeah, but the thing is, if it's at a certain height and it's emitting light back at you, and you are under cover, that is lower than it. The light of the angle would never actually reach your eyes unless the plane was below that height.
That's not true.
Why?
It can reflect off of the bottom of the clouds.
Yeah, for it to reflect off the bottom of the clouds, it needs to be below the clouds to even.
And it is for what you for your apparent position. It is below the clouds, right? I mean, look at this image. Do you get what I'm saying? I'm not trying to say that anything about flat Earth. I'm not a simple observation that I'm trying to point out to you.
Yeah, and I'm pointing out third grade geometry that says it's wrong.
Yeah, but the geometry goes against this picture, right?
Right? Okay.
No, I'm just saying that
this picture is okay because the Earth is actually round. So the light source would be perpendicular or even under.
I'm going to give you this thing again here. What I'm trying to say. Whoops. Am I on there? Let's see here. Can you see that?
Yeah, it would be accurate if the sun was above the clouds.
Okay, but then that's a fake picture.
It's not.
Right?
How is it fake?
Because in the picture the sun is lower than the clouds, right?
Yeah, and
you're trying to mix two different things. You're trying to imagine the sun, and you're trying to line these things up on a piece of paper geometrically, when in nature, and this isn't about a curved Earth. I'm saying that anything, a jet or anything, can be like, how does radar work, and how does what is it, ham radio skip propagation and things like that? It's because they can reflect off of something, the ionosphere, and skip it back down or bounce it back down, right?
Yep.
And of course they think that's going around a curvature or something, but what I'm saying is this is okay. The image, just because the clouds are pink on the bottom, does that mean that the sun has to be lower than the clouds?
It doesn't have to do with the pinkness of the clouds. The shadow is pointed up. No,
the shadow's just okay. Look at the image. Okay, hold on. Let me I got a thought experiment here for you really quick. Okay. Tell me, in this image, is the top of the mountain or the sun higher? What's higher?
Well, in this image,
the mountain. Simple answer. There's a reason why I'm saying that.
They're not.
What do you expect to see? Do you expect to see the shadow going a different way, like down to the ground, when the sun is way down there? It would have been 2 hours, 3 hours earlier that the shadow would have been pointing, down at the ground, right? Because the sun would have been up right about here. So it would have been higher. And as the sun goes further away or down or whatever you want to call it, the shadow is going to move. And of course, it's going to be on the reason why the shadow is there is because the sunlight is not able to hit the bottom of the clouds, because the mountain is in the way.
The clouds are above the mountain.
Yes.
Yeah.
But the sun is below both.
So for you to get an angle of so you have, if you have your folder, right?
Yep.
You have it flat. And then you have a light source, and put your finger under the folder.
Okay.
Or not touching it, just a little bit below it.
Oh, okay, like somewhere down here or whatever.
Yeah. How would you get a shadow onto the folder?
By putting the light down here. Watch. By putting the light. If I put the light, let's see, I'll use my microphone. Okay, are you guys?
The light has to be below.
Hold on. Yeah. Okay. So, how was I going to do this? Okay. So let's say my microphone right here is the part that's below the cloud deck or whatever we want to call this. And so the sun, it's up here, and the
Yep.
sun's always up here.
Yep.
But as it goes further away, and we know this, it gets lower and lower.
It doesn't physically get lower.
No. Listen, I don't care what it does physically. Doesn't matter what it does physically. I'm trying to point out to you there's something you're in denial of, and it's a simple thing that you're observing right now. And you're still saying, no. You're shaking no at it. And I can tell that you're thinking that this is curvature or flat earth thing. This is a simple observation that any artist that does any drawing needs to know. Anybody that does, I guess what I'm saying, just because the light source is above like this, above this part, as this thing goes farther away, I mean, let's exaggerate it. What if the light source is just a little bit above this?
Yep.
And you move it like this.
Yep.
And you're shining that light. My hand is going to get hit with light from the bottom of this because this, as it goes away, it goes.
Yep.
That's, I don't know what the word is to call that.
It would never go up.
It would never go up. No, it's, I guess the light isn't going up. It's just going over or whatever.
In this picture, the light is going up.
No, it's just going from the sun to the mountain.
Which is
There's a
casting a
direct
shadow
line.
upwards onto the clouds.
Okay. What you're doing is you're taking the sun and you're placing it up in the sky or 93 million or whatever. You're placing it higher than the clouds when it's clearly not higher than the clouds. It is in reality, but in this picture, you can see that the sun, just take a straight line. Let's see here. I might even have a way to do this. Just take a straight line and draw it from the light source to the top of the mountain. And those are the two lines that you're going to get.
Yeah.
It's below the mountain. Apparent position is below the mountain.
It's
There's
not
no other
apparently below it.
What?
It would have to be below it.
No, I'm saying that it doesn't matter if it has to be below it or not. In this picture, it's clearly below it.
Exactly. So how does that work on a flat plane?
How does when I walk away from you, how does my head go lower as I walk away?
It would never physically go lower.
No, it doesn't have to physically.
The angle
you watch it go lower.
It would never
Draw
go
a line in the camera, and I start walking away from that camera. I will go below that line at a certain distance. My head will dip below that line at a certain distance because of the angular size of me shrinking as I walk away.
You would never. So the law of perspective states that parallel lines will appear to meet at infinity. They will never go below.
Obvious, but if we're not talking about parallel lines or anything, we're just talking about an image where you have the sun at wherever, and you have a mountain here. Draw a line from the sun to the mountain and continue the line, and you're going to get right there. The sun can't get past that mountain to be hitting that. Actually, it's a reflection to your eyes. The mountain or the sun can't light up the clouds there because the top of the mountain's in the way. And yes, the light is coming from lower than the top of the mountain from where we're standing. Physically, the sun is obviously higher than the mountain, higher than the clouds.
It doesn't work geometrically.
I don't care. We're looking at it right here. We're watching it, right? I'm just pointing it out. You're in denial of like a simple observation.
Only way for this to work, right, is if the light is coming from below the mountain, so it's going up, right? So There's two ways this can work, right? And I'll explain it both on a flat plane and on a globe.
Okay.
On a flat plane, the sun would have to be below the clouds, which is observed nowhere. On
It's
a globe,
observed in the image.
the cloud is not physically below the clouds.
No, but the light source is what I'm saying is the light source is clearly lower than the clouds in this image.
Exactly.
Yeah. So
on a globe,
no,
right?
Okay. I understand where you're going with this, but that's a ridiculous thing because
It's
you're
not.
trying to tell me that the curvature of the earth is so close to you and that the earth is so small. Because you're not understanding the size of the earth if it's a 25,000 mile circumference sphere.
That's not what I'm saying at all.
You're saying that the sun's going down beyond, or that we're going back like this, and that the ground is that our line of sight tangent covers up the sun. That's what you're saying.
Yeah, and then the angle will go up.
That's
It works.
no, that's an explanation.
Of
That's an interpretation. That's what it is. It's an interpretation. I believe that interpretation. So I'm not arguing with that. I'm saying it's an interpretation, but it's not going to get you anywhere to say to be looking at an image, the one that's behind me, and to see that the light source is lower than the mountain, and then to think that the shadow is for any other reason than the light source being lower than that mountain and lower than these clouds. It has to be this way. If the light source was up here, it would have been 2 hours earlier. Do you know what I'm saying? If the light source was higher in the sky, so whether the sun is going down a curve or whether it's going further away, same result.
No, it would not be the same result.
It is though, because the sun in this image, put it this way, where is the sun in this image?
In this image, it's 93 million miles away.
But where's the sun in this image? I'm saying if we were going to put a circle on it, I can try to do that.
Well, it's
because the sun's only in one kind of area of this image, and that's like right here, somewhere in there.
Yeah.
And so from the sun to the mountain, we get those angles there, right? And let's just say there was no clouds right here.
Yep.
And there was, well, that doesn't help. I guess what I'm saying is, what do you expect to see as the sun either goes down or further away? Doesn't matter if it's curved or flat. What I'm saying is, as it goes further away or down, and let's say, let me get a fake sun. I got an idea. Give me a moment. Go ahead and kind of say something about what I'm not trying to I'm just trying to just show you a simple observation that we make in reality. And it's not physical reality, geometry that's going to be able to explain perspective. Because this perspective, if you look at there's things that are compressed as we look farther away. As they get closer to the ground, the atmosphere, everything, it compresses everything. That's why we see so many different kinds of sunsets where the sun's setting above the horizon and all these different, I don't know what you call it, different ways that we see these things through different mediums and through different weather and stuff. Whoops, NASA, where did that come from? I'm looking for an image. Go ahead and tell me what you think.
I don't. You as an observer on the ground does not matter.
It sure does.
How?
That's the only way that those clouds can be lit up on the bottom is if we're observing from that place with the sun at that time of day, that low in the sky.
Yeah.
Yeah. And it doesn't matter if it's going beyond the beyond the horizon, or if it's just going further away. It's the same thing.
If it goes further away and it's above the clouds, right? It's physically above the clouds.
Yes. It's always physically above the clouds. Always.
then how does an angle
Let me,
up underneath?
because where is the sun? The angle is only coming from, because there's an observer. If there's no observer there and no one's looking from there, there's no shadow, there's no anything, because the light has to be coming like to your eye or to, do you know what I'm saying? I'm looking for an image here.
So if there was no one to observe this, would it happen?
If what?
If there was no one to observe this, would this happen?
Well, that all depends on how you look at it. In fact, it doesn't happen if no one is there to observe it. That's a fact.
So if a tree falls in the woods, it makes no sound?
If there's no one to hear it, there's no sound. I'm not saying that it can't make sound. I'm saying if there's no one to hear it, there is no sound. There's no one heard a sound. Like, if trees can hear, maybe then. But do you know what I'm saying? If there's an observer, that's what it's relative to. That's what everything's relative. Now, the sun being higher than the clouds, if you take a cloud that's at 7 feet and the sun goes down and the sun is below that 7 feet from my eyes, there's no reason that the sun can't hit the bottom of that 7-foot cloud and bounce into my eyes. Do you get what I'm saying? The sun's much higher than that cloud, but not to my eyes. The sun is lower than the cloud to my eyes. Do you get what I'm saying? It's very important to separate the two, because we are talking about a relative to the observer, you know? And that doesn't go against the sun being higher than the clouds. It works. It just always is. If you have the curvature of the earth and that's what's you think is causing that angle, well, just go over to, 2 time zones over and the sun is still above the clouds. It's always above the clouds. You get what I'm saying, right?
Yeah, you would. It is always in your model, right? Or do you have a model?
I have the observations we make.
Is the sun, how far away is the sun from Earth?
The sun is celestial. I'm just giving my beliefs or what I see it as. The sun isn't. It's a disk, according to Scripture. It's a great light to rule the day and to govern all that. You know all that stuff. What I'm saying is, the sun is heat. We get heat from the sun. We get light from the sun. And the sun comes up in the east and it sets in the west every day for every observer on the planet or the plane. Right?
That does rise and set?
Yes, for every single observer.
Yeah. So for the light source in this picture,
Mm-hmm.
so just the angles. Ignore your observing and that all that stuff, right?
Mm-hmm.
If
you're talking more the geometry.
Just straight geometry.
Yeah, it won't work that way. It won't work on straight geometry. If you're trying to draw straight lines, well, I take that back. Because of the way that light works, it will work because it reflects off the bottom of the cloud or whatever. It's. Do you know what I'm saying? I'm trying to find this other image and I'm not having luck.
Well, the light, so if you have your notebook and you hold it up there, for you to get light under it, you have to have the light coming from under the notebook.
The light has to be lower than the notebook.
Yes.
From my eyes.
It doesn't matter. You're seeing it.
From my eyes, because the light can be up here. You're never going to see it at the bottom of my hand.
Yep.
That's what you're saying. And I agree with you. Okay. I'm saying there's another observation that shows us that the geometry don't mean squat. Whether it's curved or flat, doesn't matter. If we're in a Walmart building and we remove all the aisles and we remove all the clothes and all the stuff they're selling. So we're in a flat floored building and I have on the far corner of Walmart, 800 feet away or however far.
Yep.
I have at the ceiling, there's a light.
Yeah.
On the ceiling, and it's 23 feet in the air. And I'm sitting on my butt at the other corner, and all I'm doing is I'm holding my notebook like this. So my notebook is only 36 inches to 48 inches above the floor, much lower than the 23-foot light.
Yeah.
Can I see that light in my notebook? Yes, I can. Actually, you know what? I have this little you probably can't see that unless I go over here, maybe.
There would always be a portion of the notebook that is in shadow unless it there would always be a portion of the notebook in shadow.
Okay, see this light right there? You're gonna have to take my word for it, but the notebook, this is how high the light is. Okay, the notebook, I'm gonna move it lower than the light. And you're saying because this is a straight line going underneath my light, I'll never see the light.
No, you can still see the light. If it's far enough away, you'll see the light.
No, I'm saying I'll never see it on the bottom of my notebook. But that's not true, because as it goes further away, it goes down to just like any object that's traveling away, it goes down. The apparent position goes down. So as it goes down, let's go back to the Walmart situation. So 23 feet, 800 feet away, it's like almost a parallel line with the floor, but it's not quite parallel, but it almost is. But that parallel line, as soon as I go like this, I can look from here down to that 23-foot tall light. That's what I'm saying. And this is only 4 or 5 feet in the air. So the light is another 18 feet above this notebook. Doesn't seem possible with geometry, because that line would have to go right through this notebook to get to my eye, because it's higher. But since it's moving farther away and we're so far away from it, I can clearly see it, because it's like right there. I mean, if the notebook ain't here, I can see the light at the other side of Walmart, and it looks like it's just above eye level or whatever. Well, when I go like this, now it bounces off of here into my eye. So I'm not saying that the geometry would work, because it doesn't, because the sun is higher than the cloud. Do you get what I'm saying? But the sun is higher than the mountain. But if you stand at the mountain, at the top of the mountain, you're going to look down to the sun. And I'm not talking about curvature or a flat. I'm just saying, just simple, looking at something far away, you're always looking at it right at near eye level, or near the horizon level. Do you know what I'm saying? Did I lose you?
No, I'm here.
Okay.
There would always be, of course, you could see the light source,
Mhm.
right? You can see the light source, but it would never cast a shadow up.
Well, it's at the ceiling, I guess. But if we remove the ceiling from Walmart, and that kept that light at 23 feet,
Mm-hmm.
and if we put some clouds right above Walmart, you're saying that I couldn't look at the clouds and see the reflection of the light? And it's not that the light is higher than the clouds, or what? That's a backwards thing that I just said, isn't it? What I mean is, okay, the ceiling for Walmart, you're saying the light, let's just say it's at the ceiling, like the ceiling's 23 feet high or whatever. So the light's at the ceiling, but it's far enough away that I can get a reflection of my 5-foot notebook. I can get a reflection off the bottom of it to my eye, but you'd never get a straight line to draw from the light to my notebook bottom to my eye.
Mm-hmm.
And it's not because there's a curve or anything. It's just because you're saying the angle. Okay. If there is we have to lower the light to 10 feet then. And we'll say my notebook's at 5 feet. And we go let me make sure I'm thinking of this right. If the, okay, so the light at the other side of Walmart's 10 feet, and let's take a 12-foot swing set that they sell at Walmart, a 12-foot tall swing set. That light at 10 feet is going to shine an upward shadow from the top. The top part of that swing set will be, the shadow will be going upward, right? Because it's higher, or it's higher than the light source. But if you move the light source up, you're saying that you can't get an upward shadow. And that's right. You're correct.
So
But if I move the light source further away after moving it up, what happens to the angle?
it
It goes like this.
will get smaller and smaller and smaller, but it would never go up.
No, it's not that it's going up. It's going from the light source, drawing a straight line from the light source to the top of the mountain, and that's where it hits on the clouds. Like as the sun goes further away, or even if it was a flashlight, as it goes further away, no matter where you are or who you are, it's going like this to your eyes see it going down and away, down and away. So as it goes down, anything that moves away from you, as it goes down, eventually it's going to get covered up by your neighbor's trees or your whatever building is between you and that sun, or the mountain or whatever. It's going to get covered up by that. So you're not going to see the sun or the flashlight or the light source or whatever. At a certain point, it's going to be too low for you to see it.
No.
Ground interference, it's called. And that's radar deals with that. You can only get so much distance because of ground interference, because of trees, mountains, and hills and buildings. Eventually, no matter what the object is, eventually it's going to get covered up by the things between you and it that are taller than you, that you can't see past. You know what I mean? And we're talking at a very, very low angle for these distances, but
that's not how reality works, though.
it sure is. I guess if you're thinking that geometry defines reality, and it just doesn't. And right here, we're actually talking very specifically about a way that geometry can't explain reality.
No, geometry works perfectly fine here.
Okay, then how does the sun that's lower than the clouds light up the bottom of the clouds? Simple.
The Earth's a globe.
No. No, look here. Okay, go back to the Walmart situation.
Yeah, I understand what you're trying to say.
Look, we could use the bill of my hat. Okay, anything we want. If there's something right here, and the sun goes down and touches the horizon, or it gets near the horizon, anywhere down lower than between here and the horizon, the sun is way higher than this notebook, I assure you. And I'm only teasing, but the sun is way up there. But if it's so far, it doesn't matter if it's far away or what it is, but my eyes see the sun go down and touch that horizon. Well, it's just obvious to me that the light can go from there, because I can see the sun. I mean, right now I can see my LEDs in here, and if I go lower, I'm not going to be able to see them until I'm far enough away that they're low enough to see. I guess it's an observation. It's not like something that
Where do you observe this?
What?
Where can you observe if your light source at a certain height that's higher than another object, go far enough away? So
anytime there's a sunset and there's clouds in the sky.
Yeah, but the Earth's not flat. That's why it works.
No, it doesn't matter. We're not talking about the Earth.
It matters.
No, Andrew,
It does.
you're only you're like locked on the flat Earth, curved Earth thing. We have to pull away from that in order to discuss this.
This photo
perspective. This is simple. This is the apparent position of a observer is a different thing than the geometry of how you or anybody sees a model. Do you know what I'm saying? A model of the earth doesn't define the things happening in the earth, the things happening with our eyes and what we're seeing. And I'm just simply trying to point out that I can have my notebook at 5 feet in the air. Now listen carefully, because you just seem to be not comprehending or not acknowledging this. I can have this notebook right here above my head, right? And I can have a flashlight at 12 feet away, just a couple 100 feet away. And I can see that flashlight on the bottom of this 5 foot or 6 foot tall notebook bottom. So the geometry does not work. We're only talking 200 feet. We're not talking about curvature. I'm talking about as that light source, as that flashlight moves away from me, and as it goes to 300 feet, now it's here. 400 feet, now it's here.
But the light source isn't actually moving down.
It's moving away, but it is moving down for these eyes.
It appears to move down due to the law of...
It does move down. I'm saying
it appears to move down.
Exactly. So it appears to move down. And so when we look at it, we see it here and the mountain here, and we draw the lines, and it only makes sense to me. I don't understand. It has nothing to do with a curved earth or a globe. That's a poor assumption. What you're doing is you're limiting yourself to this locked in idea that doesn't make any sense. You're obviously going against simple observation here. Do you see what I'm saying? I'm trying to point out that it's not an idea I have. It's something you can witness every day, all day long. You can do experiments. I'm not saying the geometry works either. I'm saying that we see something, and when there's distance involved and everything's designed, and our eyes are designed in a way to understand these things. And of course, there's things we don't know, like is the earth curved or flat or what, all these things. But what I'm saying is a simple observation. That's all. And if you go against it, then I don't know what to say to that. That's like really weird to me.
So I'll do this.
Okay.
I'll put a flashlight in my basement, right?
Mm-hmm.
And I'm gonna set it quite high. And I'm gonna go about 100 feet away.
Okay.
With it in a item that is flat, and it's gonna be below the light source.
Okay.
Only by slightly. You would not see it casting a shadow up.
You'd have to have the same scenario that you have in this image behind me in order to get that shadow. Is the light source? What I'm saying is this shadow is only here to this single position. If you move positions, the shadow moves, the sun moves, and the mountain moves.
No. If I walk under the shadow's still gonna be there.
But it's above your head now.
Yeah.
It moved.
Still physics. Well,
where's the sun? The shadow's above your head, and the sun's behind the mountain. You can't see the sun because the mountain's like blocking it and you're under shadow. So how is that not comprehensible? Because the sun isn't. It doesn't have to be physically lower than the top of the mountain to look lower than the top of the mountain. And that's what we're doing, is we're looking. It's an observation. The sun has got light coming, hitting things. We're looking at it from a single place. If we can't look at it from more than one place. I mean, we can if we take pictures or whatever. What I'm saying is these pink clouds are not actually pink. And if you went up to the clouds and you were able to sit inside of the cloud and see, does this cloud get pink? It doesn't get pink. That's what the observer sees. Do you know what I'm saying? The cloud itself is not getting pink.
Why are we talking about the clouds being pink?
Because that's behind the shadow, or the shadow part, they're not pink, or they're not lit up whatever you want to call it, reflecting light.
The light is red.
No, the light is the sun, right?
Yeah,
It's
yeah. The
going
light's
through a
traveling
bunch
through
of
the
crap.
atmosphere, and it's red.
Going through a bunch of crap, and it's turning it to a reddish color.
Yeah, which is hitting the clouds and coming to our eyes.
Exactly. So the light source is lower than all that stuff. So when it comes and it goes and touches that stuff and then comes to our eyes, this is what we see. I don't think that it's obvious to me that the sun in this image is lower than the top of the mountain in this image. And so in this image, forget the geometry. In this image, we're seeing clear geometry from the light source, drawing straight lines out with perspective. And that's what we see. I guess you're seeming to have to like get what's the word I'm looking for? Stumped or whatever, because it's hitting the cloud, because the angle goes up. Has to go up. Because the sun is let's just say the sun was sitting on the ground. Okay.
Yep.
Let's say it's not going behind. Let's just say it's just behind these mountains right here.
Yeah.
Okay, so it's not down past the horizon. Okay. It's just out of our view though, because those mountains are covering it. So right there, that proves that those mountains can get in the way of the sun and give it that angle and make that shadow go on the top of the clouds.
Yeah.
I'm not saying the geometry works. It doesn't have to work. The geometry is just an idea. That's all it is.
It's not an idea.
Well, what about where does that geometry come from? It's a different thing. It's a different subject or a different science or whatever you want to call it than an observer observing. You're trying to look at everything and understand it all as one thing. And I'm telling you that I don't think that's possible, because go back to the Walmart one. How can I see the sun? How can the sun reflect off of this 6 foot tall notebook when when the light on the other end of Walmart's way up here?
It can't.
There's no geometry that can make that work.
Yeah.
But Andrew, if there's a light 20 feet in the air that's 500 feet away, and I go like this, and this is held level, do you think it's going to be possible to see that light in the reflection? I'm just saying, if I go like this to the camera, I'm going to see from my eye to here to that 23 foot tall or 20 foot tall light, because the 20 foot tall light is lower than this point. It's down here.
Yeah.
Of course, I can see the light go like this. Right?
Yeah.
And that's in a flat floored Walmart or a curved, whatever you want to call it. I'm just saying
you can see the light.
Yeah, and
that
you
see.
I'm sorry, I cut you off.
I'm not arguing that you can't see the light under the clouds. That's not my argument. I'm just saying you can't have it go up.
Well,
light moves in straight lines.
If you have a light on the floor and you have a Tonka truck here and it's taller than your flashlight, it's going to go up, right? That the shadow will go up. If you shine the light at the truck, it'll go up because it's lower. It doesn't have to be down a curve to be lower, because it can be up here and it's still going to be lower. It's above the Tonka truck, but as you move it far enough away, what happens to the angle? The angle goes like this, and pretty soon it's not physically, not geometrically, but to your eyes or an observer, in reality, it is visible. That's what I'm saying. It's lower than than what the clouds or whatever we're talking about above us. That's higher than it in reality.
And I'm saying that's impossible.
But it's not, because
why?
Go to any building. Okay, go out to your street and look at the street light, measure the height of the street light, or you don't even need to measure it. I'm just saying, at the far end of the street, go look at the light and say, okay, that light is 12 feet in the air. And then go like this. Take a notebook, hold it you're about 6 foot. You're pretty tall, aren't you? I'm guessing you're more than 6 foot, maybe. I don't know. But hold it at the top of your head and tell me if you can see the light bouncing off of the notebook. You'll be able to see the light.
I'll certainly do that.
And yeah, it's only because the angles, because because I agree with you. Geometrically, it doesn't work. If the sun's here, you can't get the light to go like this if the light is a straight line. It has to be a curved line like this, right?
Yep.
And so what I'm saying is the geometry makes no sense, but observing is different than what the geometry shows us clearly, because I can get a straight line to go from that light that's up here to hit the bottom of my low notebook and go into my eye.
Okay, so
that's what I'm arguing is what we're seeing in this image. It's just it's the apparent position of an observer, and if we change our apparent position, the image changes.
here I'll go out and I'll do some of these observations.
Okay.
Right. I'll set up experiment. I'll film it and stuff, and maybe develop a low grade video.
And I will try to actually do a couple. Try to do like a simple demonstration of what I'm trying to like. I can just do it on my street. I have a street light that's way down by this park.
Yep, same.
I do that because really it doesn't go against any science. It's I don't know all the correct terminology, but the apparent position of something in an observer's view, that's all that counts. If we're talking about angles of light and what's going to be visible to that observer, that we all know that the sun is higher than the clouds. And even if if the sun is going over the curvature of the earth, and actually like we're moving like this and the sun is like just going like this, right? What's actually happening there doesn't matter if there's curvature or if it's perspective. It's the same thing.
They would give you different outcomes, but the one in this picture,
well, the angles are the same. I'm saying the angles of the light coming to the observer's eye.
That geometry works in this picture because the earth is a globe.
Except that there's no curvature of the earth is what that is the whole point why everyone's talking about this at all, is because water, we can look at water and we have some sweet optics that look much further than like, I mean, the example everyone always uses is that the skyline of Chicago from the other side of the lake. That's like the tallest building's like 14 or 1500 feet in the city, and it's supposed to be 2,000 foot of a hump or something that you can give all of your light bending and all you want, but that's not what's happening. That what's happening is we can see a certain distance and everything down on the ground, and there's plenty of reasons for this, but it's compressed. It's always way compressed. So you don't see like your blink test idea. That doesn't work.
It does work.
No, it does not work. If you look at if we go to Elk River and we go up to where those sand pits are, and you can see downtown Minneapolis skyline from there. Take a image, and you can see the windows at the bottom of your image of the buildings. And I'm talking 30 or 29 some 0.67 miles away or something. The bottom of the image is shrunk way down. It's half the size of the top of the image, the top of the building.
But why?
The floors are all the same size.
Compressed.
What's that?
Why isn't it all compressed?
What are we looking through?
The air, but it should uniformly compress the entire image.
No, because if it was uniform, that would mean we had a perfect gradient We don't have a perfect gradient. It way thick atmosphere down here. And
Yeah,
so if you're looking 30 miles, just keep in mind that your apparent the angle that you see the top of, say, whatever height is way right on the ground again the further away you go. So you're looking through the worst, thickest part of the atmosphere if you're looking at anything on the ground, especially over water. So you get it's magnified over, or I mean it's multiplied over water. So and a lot of this, it all comes down to the assumption that Earth has curvature. And that would be like, obviously my argument is that there still has been no way to verify curvature. There's a lot of holes in these numbers because like we see a perfectly flat plane and we measure the farthest we can see, and it's like the distance left to right is, I don't know how many miles, hundreds of miles, 100 miles from left to right, the furthest things we can see. And there's no curvature there yet. 3 miles away, you think you can start seeing a ship go over a curve, but that's not what's happening. The ship is getting smaller, angular size, and it's going away from you. And the bottom of the ship is going to be overtaken by waves and the thicker part of the air. And eventually you can't see it anymore. But water's flat. So that's my spiel. You go ahead and say whatever you feel like saying, but I suppose we better eventually get off, right?
Yeah, I mean it's almost 1 a.m. Good discussion though.
Yes, for sure. And I hope I'm not being too abrasive or something. I'm not trying to be.
Nonsense.
Some of these things I think are simple, and so simple that I think all of us naturally don't believe the actual thing that we experience. We don't, because like right now, the geometry, I'm telling you something that you might disagree with. I'm sitting here telling you that a light from a higher object can somehow magically get to the bottom of that object and into my eye without going below that object. It sounds funny what I'm saying.
Yeah,
It's reality, what I'm saying.
It's not reality.
But it is. I'm saying that, look at the picture behind me. That's
you
what
can't point to that picture for reality because it makes sense. That picture.
No, you're appealing to, you're not appealing to science or that, you're just appealing to an assumption that we live on a curved ball, but there's no proof of this curve.
So for this to work on a flat plane, you need to do the magic crazy geometry that doesn't work for this
there is no geometry. You have to make an observation. Look at the picture. The sun's down there. The clouds are up there.
Okay, so I'll do some observations with that.
We'll talk about it. Yeah, I like it. We'll continue.
Because that's very easy to do. Yep. And I'll come back on and show the results, I guess.
Okay. Yeah, that'd be great. And I'll do a little goofing around and see if I can't come up with something too. But yeah. I guess here's one thing I'll say is, if you take a globe model and you take a sun and you do some demonstration, we can make this picture with a globe model, right?
Yep.
Okay. What I'm trying to tell you is that doesn't prove curvature, or that doesn't prove that the sun is going lower than those clouds. What it proves is that a model with this and that and this and that can work, can demonstrate or can duplicate or can recreate or the model or the image that we see.
Yep.
But there's other ways to recreate the image, and nature already does that. And that, what I'm saying is, we can shrink the scale down enough where we don't have to argue whether this image is talking about a flat earth or a globe, because we're just talking about the inside of a Walmart if we want.
Yeah, I'll go and do those observations.
Yeah, me too. So, all right, man. Thank you very much for hanging out. And sorry, the chat, we kind of got, there's a lot of chat. So thank you guys all for hanging out and showing up. and we'll do this again. Let's try to do it soon. How about?
Yeah.
Like maybe we try for the weekend or maybe early next week or something. Who knows?
Yeah, I don't see why not.
All right. I'll and then I'll get Alan back in so you guys can have a little more time to chat too. So
Yeah, it was really fun having discussion with him as well.
yeah, I enjoyed it, and thank you very much, Andrew.
No problem.
All right, we'll talk soon.
Peace, bro.
All right, thanks, guys. Have a wonderful night or morning or whatever it is to you guys. And thank you for hanging out.